All right, so we're going to start by looking at section 5.1, which is on exponential functions. And we'll start out just by looking at something that is an exponential function and something that isn't. So we're going to look at these two things, x squared and 2 to the x. Does anybody know which one of those is exponential before I tell you?
X squared.
X squared is a polynomial. So polynomials are a different category, which are non-exponential. So it's the 2 to the x. Right? But in both cases, you have a base and an exponent. So the base is the number that's written a little bit lower. The exponent is the number that's higher. And the key for something to be exponential is, well, two things. First of all, you have to have a variable that's an exponent. And the second thing is you have to have a base, but the base can't be anything. Specifically, it has to be a number that's a real number greater than or equal to 0. So a positive real number, but it can't be 1. We'll talk about why it can't be 1 in a little bit, but if you think about 1 to the x and what would happen with that. So your base can't be 1. So when the variable is in the base and the exponent is a number, specifically a non-negative integer, that's a polynomial. So x squared, x cubed, 2x to the 5th minus 3x to the 7th, things like that. Those are polynomials. Okay, but when now you put the variable as an exponent, and the base has to be a positive real number, except it can't be 1. That's an exponential function. Now, why can't the base be 1? Like, what would happen if you wrote an exponential function like 1 to the x? What would you get? No matter what you plug in for x. Yeah?
It's always going to be 1.
It would always be 1. Okay? Exponential functions are not always equal to a constant like that. If it always equaled 1, it would look like a horizontal line at 1. Exponentials usually have to look like this. That's an example of exponential growth. That's an example of exponential decay. So the key for exponential, variable in the exponent, and the base is a positive real number, but not 1. 1 is kind of the dividing point between whether something is going to grow or whether something's going to decay. Think about if you multiply a number that's bigger than 1 by itself over and over and over and over. Or multiply a fraction by itself over and over. Okay? One of those gets bigger, one of them gets smaller. Okay, so the domain for all exponential functions is negative infinity to infinity, as long as the base fits this condition. The base is a positive real number, not equal to 1. So if you pick a number that fits that condition, 2.6. You can raise 2.6 to any power you want. You can raise 2.6 to a positive number, negative number, 0, fractions, decimals, anything you want. What gets really weird is if the base becomes a negative number. We don't look at that at all because it's not exponential, but I'll talk about it in a second and what would happen.
What is the E in that part thing?
Element of.
All right.
A is an element of the positive real numbers. Let's look at what happened if you had something with a negative base. Okay, just off to the side. Okay, just watch this. You don't have to write this part down. But if x is 0, anything to the 0 power is 1. What if you let x be 1? What's negative 2 to the first power? Yeah? To the first power?
The first power?
Yeah.
It would be negative 2.
It would be negative 2. Yep. Anything to the first power is itself. What about the second power? What's negative 2 squared? 4. So now we get that. What's negative 2 cubed? Negative 8. So it's really weird because what's happening is the graph is, the y values are bouncing back and forth between positive and negative. And that's just with integers. Watch what happens if I try to do a fraction. What does it mean if you raise something to the 1/2 power? It means to square root it. And the square root of negative 2, you can't even do that. So now you get an imaginary. But what's weird is you could raise negative 2 to the 1/3 power. Because 1/3 means to do a what? A cube root. So cube root is fine with a negative number, but a square root isn't. So if the base is negative, you start getting really weird things that happen. Some fractions work, some fractions don't. It's really weird. So we're not going to spend any time dealing with negative bases. And if you try to graph that, you won't even get a picture. You can't even graph that. So these are examples of what proper exponential functions would look like. That one up above, that's an example of what is not an exponential function. Because the base is not a positive real number. It's a negative number. Okay? So these are all ones where the base is a positive real number. And the exponent is a variable. These are examples of things that are not exponential functions. And if you wanted to include one more in that list, you could write that one down as well. The first two are polynomials. The second one, well, it's got a polynomial in the bottom and it's got a radical function in the top. So it's definitely, it's not a exponential function. Any questions on what makes the top three exponential and the bottom three not? All right. So let's look at these two graphs. The graph of 2 to the x and 3 to the x. What I want to do is compare which one is on top. And this might be kind of like the roots. Okay, maybe one of them is on top at a certain point and then they switch places. Let's start with zoom 6. And you can see that it's curving up very, very quickly. And I think after the y-axis, it's pretty clear which graph is on top. Okay, the red one. 3 to the x is on top because 3 to a power is always going to be a bigger number than 2 to a power. Okay? After the number 0. Okay. Now, both of them, as you start heading towards the left, you'd be using negative exponents. Negative exponents cause you to flip your answer. So let's say I did 2 to the negative 4. That means 1 over 2 to the 4th, which is 1/16. Okay, very small number. As this exponent gets more and more negative, this fraction is going to get closer and closer to what number? Alyssa?
0.
It's going to get closer to 0. Like if you did 2 to the negative 100th, that would be 1 divided by 2 to the 100th power. Very, very small, but it will never reach 0. But these two graphs are kind of blending together. I can't really tell which one is on top. So let's set our y min and max from -1 to 1 so we can focus on like a rectangle right in that area. Let's try -1 to 1. Hit graph. And now I think you'll be able to tell that the blue graph, you know what, if I set it a little higher, it might get a little better. Let's put it on 2. Okay, so before 0, the blue graph is going to be above the red graph. After 0, the blue graph is below. They switch places. Okay, I don't really want to spend a ton of time analyzing that, but that's basically the behavior. So both graphs cross at the point 0, 1. In fact, every exponential function goes through the point 0, 1, because anything to the 0 power is what number? Yep, 1. The only way it wouldn't do that is if you took the graph and shifted it, okay, which you can do. Shift it up, down, left, or right. But basic exponential graphs always go through the point 0, 1. So I mentioned this idea earlier, that if you raise something to a negative power, to get rid of the negative, you flip it. Well, when we're dealing with exponentials, they're going to ask us to compare graphs, and you might have a negative power. Well, we don't want that. Okay, when you compare exponentials, it's easier if the exponent is always positive. And we can rewrite it so it is. I'm going to show you how. So, if you think about that one, what number is in front of x in that example, even though it's not written? Yeah?
1.
A 1 with a negative. So you could really think of this as a to the negative 1 times x. Now, there's a rule for when you would take and multiply two numbers together in an exponent. Does anybody remember when that rule comes up? When would you have a case where you would need to multiply together two numbers when you're dealing with exponents? And you have, yep,
An exponent to an exponent.
an exponent to an exponent, or a power to a power. So what I'm going to do is I'm going to think of this as a to the negative 1 to the x. That's, I'll write it a little higher just to be clear. That's a power to a power. You would multiply those together to simplify it. But now, we just said earlier that a to the negative 1 is just 1 over a. So the final step to simplifying that is to make it 1 over a to the x. So, the shortcut, when you have anything raised to a negative, let's just do negative x. If you want to rewrite that so it's a positive x, look at your base and flip it so it becomes 1 over. And the exponent turns into a positive. That's how you can rewrite something that has a negative exponent. Take the base. In this case, a is 5, so let me actually fill that in. So 1/5 to the x. If you want to double check it, graph what's on the left in y1, graph what's on the right in y2. They're exactly the same. Any questions on how to do that? Okay, so let's try it on this one. They want us to compare these two graphs, but the best way to compare them is if the exponents are both positive. So how would I rewrite 2 to the negative x with a positive x? Yep.
In parentheses, 1/2, and then the x.
Yep. So 1/2 of the x. Any question on that? Now the key, and we're going to get into this more later, is if the base is bigger than 1, it's going to look a certain way. If the base is less than 1, it's going to look a different way. And now you can make that comparison where before it looks like the base is 2 on both. But it really isn't, because that negative exponent is kind of distorting how it should really look. Okay, so that's how we should write it. Right, so let's graph them and see what we got. We've got 2 to the x. Just because it's easier for me to type it in that way, I'm just going to type in 0.5 to the x. If you want a fraction, just put it in parentheses. Okay, we'll do zoom 6. All right, so 2 to the x is in blue. The other one is in red. So that one's blue. G of x is in red. Right. Does anybody notice those two graphs? If you kind of look at them, what do they kind of look like? Like if you think like transformations of each other. Yeah? Yeah, it is. The blue and red one are reflections over the y-axis, and I'll prove that in a little bit. It's very simple to show that they are reflections. So, what I want to do is, looking at those graphs, find the domain and range of each. Let's start with the domain of f of x. So the graph in blue. Looking at the graph or the original equation, anyone think they can tell me what the domain of f of x is? Yeah?
Negative infinity to infinity.
Yeah, it's negative infinity to infinity. The blue graph is going to go left forever. It's going to go right forever. Why? Well, look at what the equation is. It's 2 to a power. Is there any number you can't raise the number 2 to? No. You can take 2 to any number you want. So there's your domain. Now let's do the range of the graph in blue. If you plug in any number you want for x, from negative infinity to infinity, now we're asking, what does y come out to? So look at how high and low the blue graph goes. Anyone think they can guess what the lowest the graph in blue goes? Yeah?
It's like just above 0.
Just above 0, right? It's going to approach it, but never reach it. If you want to try it, look at your table. Plug in some negative numbers and focus on the column in blue. At negative 5, you're 0.03. Okay, negative 10. Now you've got so many zeros that it's doing scientific notation. That's like 9.8 times 10 to the negative 4th. Okay, somebody in the last class asked about that. They weren't sure. That's just scientific notation. All right, so as you get more and more negative, now that's 3 times, or roughly 3 times 10 to the negative 8th power. Very, very, very small, but still not 0. Okay, and what about the highest that the graph in blue goes?
Infinity.
How high?
Infinity.
Yeah, infinity. As x gets bigger and bigger, you just have 2 to a bigger and bigger power. Okay, so that's f of x. Now let's do the same thing for g of x. What does it look like the domain is for g of x? Yeah, Shannon.
Negative infinity to infinity.
Yeah, because you can take the number 1/2 and raise it to any power you want. Positive, negative, fraction, decimal, 0. It's always going to work. And because these are reflections of each other over the y-axis, the range is the same. Okay, 0 to infinity. Okay, so any questions on that idea? Now, I know I did it specifically with the case where a was 2, where my base was 2, but we can apply that idea if the base was anything. It could be 2 to the x, 3 to the x, 5 to the x. So let's just summarize what happens in general. Okay, so let f of x be a to the x, and let g of x be 1 over a to the x. Okay, a would be a positive real number. Okay, I did it with 2, but it could be anything. So let's start with f of x, which is the graph in blue. So Scott, as x approaches infinity in the blue graph, so as we head to the right, what's happening to my y value?
0 would be approaching 0.
I agree, we are going to approach 0 for the graph in red, but the graph in blue...
It's approaching, wouldn't it just be approaching...
It's either infinity or 0. Infinity, right? As you head to the right, the graph is going up.
Oh, I was looking at the red graph, that's why.
So now, again, looking at f of x, which would be the graph, could be similar looking to the graph in blue, because that's specifically the graph of 2 to the x. But anything 3 to the x, 5 to the x would look similar. What happens as x heads towards negative infinity? What happens to my y value there? Yep.
Which is 0.
That approaches 0. And now looking at a g of x type of graph. Okay? G of x is a 1 over some number. You can look specifically at the case where g of x is 1 over 2 if you want, and that'll give you an idea. But what happens in the red graph as x approaches infinity? That approaches 0. And then as x approaches negative infinity, that's when your graph heads up. It approaches infinity. So the whole key here is the base bigger than 1, or is the base a fraction less than 1? And again, it'll never be negative because I said we're not dealing with negative base. So, if you have a base that's greater than 1, I think I said it earlier, that's called exponential. Anybody know what it's called if it goes up? Yeah?
Growth.
Right. So greater than 1, and we're going to get into it later. I'm just kind of telling you now what it's called. What about if the base is between 0 and 1? Decay. Exponential decay. Okay, so two types of exponential functions. Growth and decay. So I told you I'd prove to you that those graphs are mirror images of each other. And the way I can do that is if you take a graph and change all the x's to negative x's, change all your x's to negative x's, in this graph, simplify it. If the answer that you get is this graph, then that proves they're mirror images. So I'm going to take, in function f, take all your x's and replace them with negative x's. Okay? Watch what happens. So instead of a to the x, I have a to the negative x. But we just went through this whole thing earlier. A to the negative x is 1 over a to the x. But look at the other graph. The other graph is 1 over a to the x. So in function f, by replacing x with a negative, I got g of x. That's the other graph. So that proves that they are mirrored images. You could also do it the other way too. Take function g and change all the x's to negative x's. Okay, I didn't write down the first step. But the very first step would be to do that. Okay, that's g of negative x. But a negative causes that fraction to flip. So what you really have is a to the positive x, which is exactly what the other graph was. Okay, so that proves that they are mirror images over the y-axis. And in fact, you can do that with anything. If you have a graph and you want to know what the mirror image of it would be over the y-axis, say you have this, and I said, give me the mirror image of that over the y-axis, just change x to negative x. Negative 2x minus 8. Okay, so if you graph 2x minus 8 and negative 2x minus 8, they'll be mirror images. Okay, how about, just kind of look at this one. Y equals x squared. Change x to negative x. What is negative x squared? What does that simplify to? Yep.
Over x.
What's negative x times negative x? Scott?
2x.
No, that's not adding.
Oh.
Square. Negative x times negative x.
Oh, it would just be x squared, right?
It would be x squared. So what does that mean about a parabola? specifically the parabola y equals x squared. Yeah?
There is no reflection of it?
Well, there is, but it's its own reflection, right? The graph of y equals x squared, if you mirror image it, is the same thing. So that's what I just got right here. The original is the same as when you replace it with a negative. And that makes sense because a parabola has a line of symmetry on the y-axis. If you mirror image it, you wouldn't notice a difference. All right, so transformations work exactly the same way they have in every function we've studied. Okay, so I'm not going to go through and explain all the transformations again, but I think by now we should know which one is the horizontal shift, the horizontal stretch, the vertical shift, and the vertical stretch. All right, so I want to know how I would transform f of x into g of x. All right, so first thing, I just want to make sure we know how many transformations are happening. Anyone think they could tell me how many transformations it would take to change f of x into g of x? If you break down every single transformation in g of x. Yeah, okay.
Are you saying how many?
Yeah, how many?
3.
3, exactly. There are 3 transformations to turn f of x into g of x. Okay. Anyone think they could tell me what number we're going to focus on for the first transformation? You don't even have to tell me what it does. Just tell me the number.
1.
We're going to focus on the plus 1. Yep. Now, somebody else tell me what the plus 1 is going to do. So you're doing a plus 1 to the x. That's kind of like doing this. You're adding it right to the x. Very different than putting it on the outside. Scott?
It would be a horizontal shift to the left.
Yep. We're going to shift left 1. Now the second thing we're going to focus on is the 2. And you're multiplying by a number in front. That would be different than multiplying by a number next to the x. Multiplying by a number next to the x is a stretch. So is multiplying by the 2 in front. But what kind of stretch is the 2 in front? Rue?
Vertical.
That's vertical. So vertical stretch by a factor of 2. And the last thing we got to look at is the minus 5. And what's the minus 5 going to do? Yeah.
Vertical shift. Yeah, vertical shift.
Can you be a little more specific?
Down 5.
Down 5. Yep. So when you describe the transformation, just make sure you tell me the direction and how much. So shift down 5. If you want to say vertical, that's fine, but if you say down, I know up and down is vertical versus left and right is horizontal. Okay. You could put negative in here as well. Like if you had a negative in front of the 2, that would be a vertical reflection. If you put a negative in front of the x, that would be a horizontal reflection. Okay. Any questions on that? So technically, there's 6 things that can happen. Okay, you get your horizontal shift, your horizontal stretch, horizontal reflection. Then you have all the vertical stuff. Vertical stretch, vertical reflection, vertical shift. And really, the stretch and reflection, you can really do those in either order. Okay? You want to make sure you do the shift first. Then you could do either one in group 2. You shouldn't get a difference. Then you could do either one in group 3. And then you could do the one in group 4. So you have to keep them in group 1, 2, 3, 4 in that order. But group 2 and group 3, you could switch within that group. You should get the same answer. Any questions on? All right. So I want to show that these two graphs are the same. This might be handy on a multiple choice question if you get a certain answer and it doesn't match what I wrote. Maybe I just wrote your answer a different way. So to prove this, you could start with f of x or g of x and change one into the other. Let's start with f of x. Anybody see anything I could do there that would start to make f of x look more like g of x? If you focus on the exponent, there's something really, really, really different in how they're each written. Anyone see, maybe?
You could divide by 2.
Okay, I'm going to do something with a 2 after. That's good, though. We are going to come back to the 2, but something even simpler before that. Yep?
We write it as -2x plus 3.
Yeah, just the order is different. Okay, one of them, the x is first, the other one, x is second. So if we're trying to make it the same, let's put them in the same type of format. So let's write it as 2 to the -2x plus 3. Now I'm going to do what Mailing said. I'm going to factor out something. Okay, I'm going to factor out a -2. The reason? If I look at g of x, what number is in front of x right now? In the exponent for g of x? 1. So let's make my number in front of x a 1. And hopefully by doing that, it automatically makes the other number match. If it doesn't, then we're stuck. Okay, what would I be left with in parentheses if I factor out a -2? Jess?
X minus 1.5.
All right, so that's good. So that part matches up. But now the next step, we want a base of 0.25. How can I jump from this to having a base of 0.25? Yep.
I actually don't know.
You sure? Jay's?
Or you say 2 to the -2.
Yeah, you can do 2 to the -2 because remember, this is a product. Right? It's a distributive property. So if you're multiplying together two things that are in an exponent, that means you must have had a power to a power. Okay, that's the only reason you would ever multiply exponents together. And now I can do 2 to the -2, which is 1 over 2 to the 2. And what does 1 over 2 to the second power simplify to? Yeah, 1/4, which is 0.25. So I really broke down every single step. You could probably combine a few steps here. Now we've manipulated f of x and we turned it into g of x. Okay? And we showed that they're actually the same thing. Also, I think g of x is a much better way to write it because I can clearly tell you what's happening. It's a decay function and it's been shifted 1.5 units to the right. Okay? It's kind of hard for me to tell that looking at the original. Okay? Some people might say, oh, it looks like a growth function because the base is bigger than 1. No, they're both decay, they're the same thing. A decay function shifted to the right. Okay. Any questions on that? So that might be something you have to do just to describe transformations. Just get it in the right format. Okay? Always we want x to be a positive number. Usually makes it easier to think about. All right, let's take a quick look at this graph. So what I want to look at here is what happens to this as x gets really big. Okay, this is going to tie in more when we do logarithms tomorrow. But since we're talking about exponential functions, this is an exponential function, you'll see the connection. Okay, as x gets bigger and bigger, what happens to just this fraction? What does that fraction get very close to?
0.
It approaches 0. Okay? But does it ever reach 0? No. So you're taking a number that's extremely close to 0. Like let's say you plugged in 1,000. That's 1/1000th plus 1. So you have 1/1000th plus 1. Very, very close to 1. And you're raising it to the 1,000th power. Now, normally if you take a number very close to 1 and raise it to a power, you pretty much just get 1. If you take 1.000000001 and square it, it's basically going to be 1. But we're not raising it to just the second power. We're raising it to an extremely huge power. So it's like there's two things kind of fighting each other. You got a number that's getting closer and closer to 1. So on one hand, you want to say it's 1. But then you're raising that to an extremely large number. So let's graph it and see what happens. All right, so we got 1 plus 1 over x to the x. So what does it look like you have in that picture that we studied last week? Yeah.
Asymptote?
Yeah, there's a horizontal asymptote. Obviously, there's a vertical asymptote at 0 because you can't divide by 0. Don't focus on the vertical, focus on the horizontal. Let's let x get bigger and watch what happens. If you plug 10 into that formula, you would get 2.59. If you plug in 50, 2.69. Didn't go up that much, considering I went up 40 units on the x. Let's plug in 500. So now increasing x by a factor of 10, y only went to 2.71. So it's starting to level off. And then going up almost to 10,000, I'm only at 2.718. So it went from 2.715 to 2.718, from 500 to almost 10,000. So it's starting to level off at this number 2.718. It actually, the proper number is 2.718281828. I forget what comes after that, but it doesn't keep repeating in a pattern. Has anybody seen that number before, 2.718? Anywhere? No? Yeah?
Is that E?
Yeah, what's the number E? Very good. How'd you know about E?
I watched a lot of math videos on YouTube.
Oh, you've seen it somewhere on a math video? Yeah. So E is the number 2.718281828. Don't think that it keeps repeating 1828. It doesn't. I forget the next digit. But in this particular graph, the horizontal asymptote is at the number E, 2.718281828. And I said this is going to connect what we do with logarithms because anytime that you deal with logarithms, okay, logarithms always have a base to them. Well, we're going to talk about a special logarithm called the natural logarithm. And the natural logarithm happens to have a base of E. Okay? So this number that we're going to use for our base tomorrow comes from the exponential function I just showed you, 1 plus 1 over x to the x. Okay, it'd be kind of weird to figure that asymptote out, excuse me, by hand. But using the calculator, it's not too bad. So generally, E would be a very poor choice for a variable this week. Just like using the Greek letter pi. We usually don't use the Greek letter pi to represent a variable, because we already know it stands for something else. Same thing with E. Okay, in Algebra 1, it's not really a big deal because they don't know about E yet. But from this point forward, probably using E as a variable, not a good idea because it stands for something else. Okay, and that's all I'm going to say about that for now. All right, so last thing we're going to look at is a few examples of growth and decay with word problems. So we're going to look at an example where we have a town that has an initial population of P, and the population is going to go up a fixed percent every year. Okay, whenever something goes up the same percent over and over and over, that's exponential growth. So like if you got a raise of 2%, and you got that every single year, eventually that would be exponential. It would take a very long time for that to happen, but it's exponential. So what does it say the population of the town is like at the very beginning? What's the population starting at? Yep, P. So at year 0, the population is P. Now at year 1, okay, the way I find my new population, assuming nobody in the town has died, because that would complicate things, but assuming everybody stays alive and the rate of increase is consistent. To find your amount of people at year 1, you take what you had before plus the amount of increase. So what's the amount of increase? That's your rate. So you take what you started with plus, and actually let me write this the same way. Take what you started with plus what you started with times the rate of increase. So if it was a 2, you could say my initial population was 50. I would take 50 plus 50, and if the growth rate was 2%, I'd plug in 0.02. And then I'd do that out. 50 times 0.02 would give me 1, plus 50 would be 51. So if you increase the number 50 by 2%, you go to 50. All right, so now let's kind of fill in this idea down below. Okay, my initial population was P, that's the original amount, plus the original amount times my growth rate. Now I can clean that up a little bit by factoring it. What can I factor out of each term? Yeah, Abby? P. And if you factor out a P, what would that leave you with? P times 1 plus R. Exactly. Now for year 2, what I just put in the red box, that is my new original amount. That's what I'm starting with on year 2. All right, so anyone think they could give me what I would write down using this idea right here for year 2? Start with what's the original amount? Melee? Yep.
P times 1 plus R.
Yep. So you're starting with P times 1 plus R plus, write the original amount again, P times 1 plus R times, and what are we increasing the population by? What was the way they said to represent it? R. So take original amount plus original amount times your growth rate. Now, let's do the same thing. Let's factor that. What do both red boxes have in common? Not everything. There's something the second box has that the first one doesn't. Jess?
Oh, I was gonna say like the second R, but like that's not in the box.
That's not in the box.
Yeah.
So in row 2, they both have in common what factor? Yep.
The P times 1 plus R.
Right, they both have a P times 1 plus R. So if I factor out a P times 1 plus R, okay, I would be left with P times 1 plus R, factor that out. In the first box, you factored out everything, so what's left there? A 1 plus In the second box, you still have something left that was there that you didn't factor out.
R.
An r. P times 1 plus r times 1 plus r. And how could we write that a little shorter instead of 1 plus r, 1 plus r? Yeah, it's P times 1 plus r squared. If you wanted to find what the population would be after 3 years, it would be P times 1 plus r. To what power, you think? Okay. To the third, yep. After 20 years, it would be P times 1 plus r to the 20th. After t years, it would be P times 1 plus r to the t. That's the exponential growth formula, where you're starting with an initial amount and you're increasing by the same percentage. Remember that your rate of increase has to be a decimal. So if it's like 6.5%, you're plugging in 0.065. Now that's for growth. There's one thing you would change in that box to make it decay. So what if I said to you the population of a certain town is declining at 3% every year? Anybody know the one thing you would change in that box? Dan? Yeah, I could make it a negative r, 1 minus r. Okay, so for decay, it's 1 minus r. P is still the initial amount, T is still the amount of time that's gone by. Keep in mind that your units have to match. So if your growth rate is monthly, your time unit better be months. If your growth rate is yearly, like a yearly growth rate, your time interval better be yearly. Okay, they have to match. Any questions on the growth or decay formula? Okay, so let's try an example word problem, and we'll use the calculator to help us solve it. So we have a town with a population of 50,000 people, and the growth rate is 2.5% per year. First, I want to write an equation, and then I want to graph it and figure out when will the population hit 50,000 people. How many years is it going to take? Okay, so let's start with our population as a function of time. Ariana, what's my initial amount? Yeah, good. Starting with 50,000 people. Times, and Jess, what's the first thing that comes in the parenthesis?
1 plus r.
Yep, 1 plus, and what's my growth rate here?
2.5.
2.5%. So how would you write that as a decimal?
0.025.
0.025. Were you going to say that, Scott? Or?
Yeah.
Okay. And then that's to the t. Now you could simplify that a little bit. Just write 1.025 to the t. So that's an exponential function. Just barely. I mean, it's just a little bigger than 1. So we're not talking about something that's going to curve quickly. It's going to curve very slowly. Okay. And now they want to know when the population hits 100,000 people. Would that be what I plug in for P of t or t? Where would I fill that in?
PFT.
P of t. That's my y. So what I need is another y. So I'll use y2 and y1. So type in 50,000 times 1.025 to the x. Should be fine without parentheses because order of operations. It'll do the exponent first. And then I want to know when I hit 100,000. Okay, does negative years make sense here? No, we're not predicting back in time. This model doesn't necessarily predict years before. It's predicting from this point forward. How many years is it going to take to hit 100,000? I'm going to guess within 40 years. If that's not enough, I'll make it bigger. The smallest my population could be is how much? Yeah?
50,000.
Can't go below 50,000. And we want to know when it hits 100,000. So just so it's not right on the edge of the screen, I'll do 120. Okay, so there's my population. You can see it's curved, but just barely. There's my line. And we're going to calculate the what? Yeah, calculate the intercept. So red, blue point, give you a guess. The intersection is 28.1, and that's about how many years have to go by. So we didn't look at solving with algebra on that one because the variable is in the exponent. We don't know how to do that yet unless you know logarithms. So we're going to do the same problem again probably next academic week, but we're going to be able to solve it with algebra rather than graphing. Okay. Any questions on that one? Yeah?
What'd you put in for the first one? 1.025.
1.025 to the x.
Alright.
Yep. So as always, be careful about your window, whether or not you should include negatives, because sometimes negatives don't make sense. All right, let's start with, let's look at an example of a bacteria doubling. Let's say you started off with 100. After 1 hour, how many would you have if it's doubling every hour? Yep, 200. Well, instead of 200, I'm going to think of it as the base amount times 2 to the first, which is 200. Okay. How many bacteria would you have after 2 hours? Yeah, 400, which is the base amount times 2, because it's doubling, to the second power. Anyone think they could tell me how many I would have after 3 hours as the expression on the right? Like base amount. I mean, I know it's 800, but I'm looking for the other way because that's the pattern we want to see.
100 times 2 to the third.
Right, 100 times 2 to the third. So after t hours, it's 100 times 2 to the t. So here's your pattern. This is exponential growth, specifically for the case where something is doubling. It just might not always be 100, whatever the initial amount is. The initial amount times 2 to the t divided by the length of time to double. Now, I put t divided by the length of time to double because let's say you had something double every 3 days. Okay, whatever you have doubles every 3 days. After 3 days, how many times will it have doubled?
Once.
Only once. So the length of time to double is 3. I said after 3 days, 3 divided by 3 is a 1. How about after 6 days? If something doubles every 3 days, how many times will it have doubled after 6? It'll have doubled twice. So it's 6 days have gone by. The period of time to double is 3. That's 2 doubling periods. So if something doubles every 3 days, and after 6 days, you wouldn't want to put in a 6 as the exponent. This is the number of doubling periods that have gone by. So we have 100 bacteria in a petri dish, doubles every hour. When will we have 350,000 bacteria? Okay, so we'll plug into our formula. Initial amount. What's the initial amount here? 100 bacteria times 2 to the t divided by length of time to double. How often is this doubling? Every hour. So it's really t divided by 1. So we don't need to put it, in this case, you don't need to put divided by 1. So after 1 hour has gone by, it will have doubled 1 time. After 6 hours have gone by, it will have doubled 6 times. So the number of hours that have gone by is the same as the doubling period. So there's your formula. And now, how would I figure out when there's going to be 350,000? Using the calculator. Yep.
You graph a line that equation and a line at 350,000.
Yep. Graph a line at 350,000. Graph 100 times 2. And that's all you need, 2 to the x. I do need to adjust my window, though, to go up to 350,000. So I'm going to do 400,000. Minimum amount of bacteria that I could have is 100. And let's look at up to 40 hours of time going by. Okay, so I didn't need to go that far. So very quickly, it's going to hit 350,000. I'm not sure what that is right there, but the intersection point is 11.8 hours. Okay, so in about 11.8 hours, you started with 100 bacteria, you'll be at 350,000. So that's an example of something doubling. Does anybody know the opposite of doubling? What that one's called? It's not just called halving, but that's kind of part of it. It has half in it, but it's actually 2 words.
Halftime.
Not half-time. Half-life. Yeah. Half-life. So half-life, what half-life means is it's the amount of time it takes for half of whatever you have to disappear. So if you had a glass of water, and you said the half-life of that glass of water is an hour. What that means is if you leave the glass full, and you come back an hour later, the glass will only be half full. If you come back an hour after that, it would only be a quarter full. And after that, an eighth. So a lot of times where they use half-life is with nuclear material. So some nuclear materials have a half-life of thousands of years, which means if you've created, say, 10,000 pounds of nuclear waste, and the half-life of it is 1,000 years, that means in 1,000 years, half of the nuclear waste you created will be gone. And then in another 1,000 years, half of that will be gone. So it takes a very long time for some things to decay. Some things decay very quickly. Depends on the substance. But the formula for half-life is very, very similar to doubling. The only change is that the base is now 1/2. Okay, so we'll finish up with just a word problem with that, and that'll be it. Okay, so we have a radioactive substance that has a half-life of 20 days. We're starting off with 5 grams of the substance. And what I want to do is find an equation that represents that. Does everybody have up to the formula? So, I'm going to leave the second part for you. So what's my initial amount here? Yep, 5 grams times 1/2 to the t divided by the half-life length. What's the length of a half-life here? Yeah, 20 days. So that means after 20 days, you have 1 half-life. 20 divided by 20 is 1. After 40 days, 40 divided by 20, that's 2 half-lives, or 1/4 of the original amount. Right, so now the question is, when is there less than 1 gram remaining? Well, without graphing it, I can tell you roughly what it would be between. That's 1 half-life. Okay, keep track of that. 1 half-life, 2 half-lives, 3 half-lives. Somewhere between the second and third half-life. So that'd be somewhere between how many days? Yep.
40 and 60.
Somewhere between 40 and 60 days. Okay, you could graph it on the calculator and get the exact answer. Okay. Any questions on that? Alright. Okay, so homework tonight, it's on 268. It's a lot of single problems, it just kind of jumps around. So it's 4 through 7, 11, 13, 15, 16, 19, 25, 27, 29, 31, 35, 47 to 49, and 57. So we'll look at that tomorrow. Also, reminder, my extra help will be after school tomorrow because we have the test on Thursday this week.